Is there a question in chat? Yeah, am I audible now? And is the screen visible now? Can somebody confirm if I'm audible?
Hello, yes, you are audible, but screen is not visible. I think you have to share the screen.
Okay, the screen is not visible. Okay, I'll reshare it.
Yeah, screen is coming now.
Is the screen visible now?
Yes, it is
Okay.
coming now.
Okay, I can see there are some questions. So we'll discuss the both the questions in the assignment. So we'll come to that. Okay. So let me start. So okay. So I'll go again. So we have covered module one and module two of the last class. We'll start with module three today. And important things in module three is the reformulation using flux density instead that will be using D instead of E. We'll look at the frequency dependent media aspect and also calculate the frequency domain results using the time domain results that we're getting now. So these are the textbook which you're following. We have covered module one.
Excuse me, are you still at the first slide?
Yes.
Because oh, you are on the first slide.
No. I'm at the fifth slide. Is the
I can see only first slide.
Oh, okay.
Yes, only
I'm
first
not
slide.
sure. Okay.
Is it with everyone, or I don't know? Maybe it's only with me.
No, no, only first slide is visible.
Ah, okay.
Okay. I'll switch my network. Okay. Maybe there's some issue with this. Can you see the second slide now?
I cannot see the screen. I cannot see any slide.
Okay. Is the screen not shared?
Yeah, now it has come, but again disappeared.
Okay. I'll share the entire screen. Maybe this will help. Now, is it fine now?
Yeah, now it has come.
Okay. I'm on the second slide.
Yes, yes,
The course outline. Okay.
yes.
Yeah. So we'll go again. So we are now in the module three. We'll start with module three today. We covered module one and two. I'll use the pointer. So the important thing over here is using the flux density instead of the electric field. We'll see how we calculate the frequency domain results and formulation of frequency dependent media. Can you see the third slide now?
Only now, only second slide.
Still
Now
the
it's
second slide. Can you see the third slide now?
yes, yes.
Yes, now.
Okay, so there is a lag. Okay. So these are the textbook which we are referring to. I'll go slowly then so that you get time to see the slide. So we have covered the review of EM theory in module 1. In module 2, we saw the formulation of the update equations in one dimension for FDTD. We also discussed about the stability, the absorbing boundary conditions, propagation through a dielectric medium, use of different sources, calculating the cell size depending upon the permittivity of the media and the frequency of the wave, which the highest frequency which we are looking at, propagation through lossy dielectric medium. Uh, you can see the fifth slide, right?
Yes.
Okay. Now in module 3, we'll look at the formulation using flux density and this calculation of the frequency domain output using FFT method of MATLAB and formulation of frequency dependent media. So we will go over a brief recap of what we have covered up till now. We'll also discuss the assignment. So can you see the slide 9 now?
Yes.
Okay. So we started with the Maxwell's equation. We use the only 1D equations with the Ex, Hy, and wave propagating in the Z direction. We use the center difference scheme to get the finite difference form of the finite difference approximation of the update equations in 2, and using that we got the final update equations like the update equations in one dimension for the electric field and the magnetic field. Now, once we had 4, we use this normalizing. So we normalize the electric field so that the order of the electric and magnetic field were same, and then using the relation between the time step and the cell size, we substituted it to get the final this particular set of equations. And using this equation, we got the final update equations for our MATLAB or Python code. So we discussed this in previous class. We saw the results for propagation of a Gaussian pulse in one dimension without boundary condition, and then we switched over then we discussed the absorbing boundary conditions. But then we discuss the absorbing boundary conditions so that we have the matching on both the edges on both the boundaries. Then we discussed the stability of the method. We saw that for propagation in the minimum time required for a cell for a wave to travel over one cell is delta t equals delta x by c naught. And similarly, for 2D case, we'll have to see for the diagonal propagation, and for generalized space, we got the time step in terms of the cell size with the Courant condition. So we discussed the boundary conditions as well. So where since we at the boundaries we did not have the values of H, the magnetic field and the electric field front towards the left or the right side, we use the boundary conditions, and we since we know at what speed the wave is propagating, we manually substituted the value of the uh, electric field. We manually substituted the value of the electric field towards the boundary nodes. For determining the cell size, we u- use this thumb rule that we need at least 10 points per wavelength. And in case of media with dielectric um, media with dielectric different permittivity, we choose the highest dielectric constant, and according to that, we calculate the wavelength, and then we determine the cell size. So there is some more. Okay, there. Yes, Priyank.
Yeah, so I posted the same question. So in the previous slide, so I have one issue like whether this causality condition has been satisfied here or not. So
Yes.
means
Yes. So the causality is satisfied in the FDTD case. Yes.
yeah, because
Which
if you
let
look at
me
the
go back to the.
yeah, if you go to the equation, so in second equation, if you look at, we have EXK plus 1. So the value
Yes.
of H by K is depending on EXK plus 1. So, and suppose we are exciting at K equal to 0. So
Okay.
how we are like defining EXK plus 1? Because before the excitation, we don't have EXK plus 1. So,
Okay. So when we begin with the simulation, like so the we uh, we assume that there is no field. So we initialize it as zero. So before excitation, so there is no field exists. So we take it as zero, and when an excitation travels, we update the E field from we update the E field according to the excitation, the pulse, and then the H field is excited. So uh, to satisfy the causality, we assume that no field exists over there.
yeah, but in the equation, like for every value of K, it is depending
Yes.
on the value of K plus 1. So means future value of K it will depend on.
No, no,
So
no. This K is the space coordinate. This is K is the K denotes the space. So K and K plus one are actually the nodes K and K and the next node to it, not the time. So this H is dependent upon the el- uh, the magnetic field is dependent upon the magnetic field value of the previous time instant and value of the electric field at the previous time instants, but for the same node, but and the neighboring node. So this is not the time instant. This is the space actually.
okay, but I thought like in space also there might be some causality or
Yeah.
I
Okay. So that aspect, we like before excitation, both all the fields remain zero, and when we provide an excitation, we update the like we in our codes we are giving the excitation on the electric field, and this electric field gets updated, and using these values we update the magnetic field. And before the excitation, the fields are zero.
okay, okay,
Any follow-up questions on that? So we are not breaking causality, okay? And for like if you want for further clarity, you can refer to the textbook by Sullivan. So there are some like lines written on the how we are not breaking the causality.
okay, sure.
Okay. Yeah. So yeah. Anybody else? Any questions on this boundary condition? Okay, so we'll quickly go through the recap and then go to discussing the assignment. So we determine the cell size based on the highest dielectric constant in the entire simulation space. And using the dielectric constant, we calculate the uh, wavelength, and according to that we calculate the cell size. We looked at the codes and we saw the propagation and dielectric. So over there we just included this relative permittivity, and uh, again we use the 1D equations to get the update equations, and from there we got the update equation for MATLAB and Python. And for propagation in lossy dielectric medium is, so for a let me check, is this yeah, so we had looked at the propagation in a lossy dielectric medium where we included the current density, which accounted for the losses, and this particular term then was included in our 1D uh, Maxwell's equation, and then we normalized it and got the update equation for the electric field, which included the loss term, and for uh, the electric field, what we used was the since we did not have the value of electric field at uh, node n, we average the value of electric field at the time instance n plus 1 and n minus 1 at the node k. So we got the electric field update equations, and there was no change in the uh, magnetic field update equation, and so we had got this. So we got this particular set of update equations for lossy media. Coming to the assignment, so I saw that in the poll. Let me see again. Yeah, so out of 7, like most of you were able to run the code. So yeah, so you'll be able to follow it more clearly. So we'll start with the one of the cases which I had asked you. What happens if you break the Courant limit? Uh, can you see the slide number 21?
Yes, yes.
Okay. Not sure. My cursor is lagging. So when we break the Courant limit, which is we use this as 0.5 over here. So you could see that there is nothing is going on in the simulation. Like the electric field values abruptly go to very large values, and then there is nothing in the simulation space. When we work at the Courant limit, you see the, the simulation is working fine, and we act in this particular case, the number of points which we are taking for the this wave is less, so we see we see the wave, but like it is like due to less number of points to reproduce the wave, and the wave seems a little bit crooked. And when we follow the Courant limit properly, we see that the wave is being approximated very nicely, and the simulation remains stable. Now, one of the questions was to what happens when we disable the absorbing boundary condition, and we had one of the questions as well in the chat that uh, why the pulse, both the pulses get a phase shift of 180 degree. So this was the update equation for our case, right? When we do not have the absorbing boundary conditions. So these were the two equations that were being used to calculate the electric field at the boundaries when there is no absorbing boundary condition. And we see there's a phase difference in both the ways on the left boundary and the right boundary. So what happens is in our code when we are using these two conditions, we if you notice the code which I shared, we were actually calculating the electric field values from 2 to KE, and we are skipping the electric field at K equal to 1. So what happens is when we had initialized the electric field value at K equal to 1, it was initialized as 0 and it stays 0. And this particular electric field value at uh, K equal to 0 is 0. So the magnetic field is being updated using K equal for K equal to 1. Sorry, for K equal to 1, the electric field is like 0 and it is not getting updated. So every time the magnetic field is being updated using electric field as 0. Hence, the electric field always remains over here 0. And um, the case when electric field is 0, we refer to that point as PEC, a perfect electric conductor. So over there, the wave gets reflected, and we see a 180-degree phase shift on the left-hand side boundary when the wave propagates. And for if you see the magnetic field update equation, we are calculating it for till Ke minus 1, or Ke for Hy at Ke is 0. So over here, when you calculate the electric field for Ke, the Ex is calculated using Hy Ke equal to 0. So for where magnetic field is 0, that point acts as a PMC, a perfect magnetic conductor, and over there the wave gets reflected, but with the same phase. So this is why in our simulation space we are seeing the 180-degree phase shift on the left boundary, and the wave is reflected with the same phase on the right boundary. Uh, was like did was that clear? Like, were you able to follow what was happening in the code? So this question was by someone whose name, like, I can't see. It's written as meeting guest. Not sure who that is. So whoever posted this particular question, can you please let me know that you were able to follow the explanation? Yeah, okay. Anybody, any question on why we are seeing this, and if you were able to, like, if you could not follow? So I guess that was clear. So we'll move to the next question. So the next question was that we had to modify the program so that it had two sources, one at KC, some KC, and so I think I have modified this as to KC minus 100 and KC plus 100, where KC is the center of the space. Yeah. So when there are two Gaussian sources, when the pulses meet, we see that their amplitude gets added, and yeah. So and this was supposed to be used like simulated for soft sources and hard sources. So this is the case for a soft source, and when the pulses meet, their amplitude gets added. That is what we see in the simulation space.
Can you please show the code how you have defined two sources? Is it possible?
Uh, yeah, I can do that. I think it should be there in the code that will be. Let me see. My MATLAB is open. Can you see the MATLAB screen?
Yes.
Is the font okay? Like,
Yeah, that's all right.
So yeah, so I've highlighted this. So these are commented over here. So these are the two lines that will use to include two soft sources. So we choose 2 points, KC1 and KC2, which we define as KC minus 100 and KC plus 100. And we define we have defined pulse as either sine, or we can define it as the Gaussian pulse. And then we add the same pulse, or we can also, if you want two different types of sources, you can also use pulse 1 and pulse 2 and define them differently, and then add them to the electric field position where to the electric field, at the position where you want the two sources. Similarly, for hard source, you'll use you can, instead of adding them to the electric field, you just directly make them equal to the excitation. Is this okay?
Yeah, it's now fine. How have you saved this video of this image? What part of the code you have written to save the video?
Oh, okay. So I did not include it to make the code simple. I did not want too many functions to be there on the screen. So for saving the video, okay, in the next code which I share, I let the video writer commands be there. If you want, I can explain right now, but I'm not sure whether it will be too much for the entire class. So essentially, if you go there, so if you have used read write of in file, so we just use this video writer function to write it in a file, and we keep a frame rate. We open an object, uh, get the frames from the simulation, write it to a video file, and then close the video file. So I'll let it be there in the next code which I share. Maybe you can go use this MATLAB help over here to search the functions which are being used. And if you have any follow-up questions, you can ask me or even use Google. It is not very difficult. Okay. So any follow-up questions, Jay, on the hard source and soft source and using two sources?
Oh, that's fine.
Okay. Anybody else? Any questions? For any queries on question 3? Okay, so we'll move to the next question. For the question 4, we were supposed to stimulate the have a dielectric slab in the simulation region and see how the waves interacted. So using a Gaussian pulse, and I've added a dielectric slab of permittivity equal to 4, or relative permittivity equal to 4. And you can see at this interface, the we see some of the wave gets reflected and some of it is transmitted. And you can see then again at this interface there was some reflection, and this will keep happening since the wave propagating will keep reflecting from both the boundaries. So I've used this patch command to show the electric region. So I won't share the codes right away so that you can try it if you have not, because it is very essential that you are able to use and modify the codes to do this. And if you are not able to, you can then look up. You try yourself, and if you are able to do it, it's very good. If not, then you can again look up to the solutions which I'll share and then see where you went wrong. You should be able to see something like this. Yeah. Any questions on question 4?
No, I have a question on question number 3. So in general, what is the meaning of Kc plus 100? So for example, 100 is a point to the right with respect to the central part, right? Isn't it?
Yes, yes, yes,
So
yes. So the code which I shared, the simulation space was divided into like several nodes. Okay, so there was supposed to be 500 nodes, which was refined, and according to that, I have shared the questions where so the KC over there will be the center of the space, that which is 250. And when I say KC plus 100, KC minus 100, I'm referring to the node at 100, node at 150, like that. So KC over here is just the node which I'm referring to.
so in one of my code, I placed a Kc plus 20. Then the
Okay.
amplitude was extremely high, and I cannot see any pulse moving inside.
Yes. So so what? Yeah, I'll go back to my previous slide. So again, also I also over here. Okay, what is happening?
But for Kc plus 50, it was all right. So, but Kc plus 50, there was multiple waves. It's like generating from the same point.
Okay. So if multiple layers are generating at the same point, I'm not sure. Yeah, what is the issue? But if the wave is going outside the region, it is because the axes have been fixed to 1 and minus 1. And if both of your sources have an amplitude, maximum amplitude is 1, so when they add up, you will the maximum amplitude will be 2, which will be outside the y limits. So if you change the y limits or make the excitation amplitude of the excitations less than, like, if you keep both of them 0.5, then you'll be able to see the total like the total sum of the amplitudes of the pulses in the simulation space. So maybe
No,
you can try relaxing the y limits or keeping the amplitude of the two sources less.
I used only one source, so, and in that one
Oh,
source, I just changed Kc to Kc plus 20. So in the code which you send me, I have not modified anything else. Exactly, just I changed Kc to Kc plus 20, and my amplitude was going much beyond the upper limit, and also just one pulse. And in the same code, when I made Kc plus 50, then yeah, the amplitude was within the range, but there was multiple waves propagating. So if possible, maybe if you have time, then you can just change in the MATLAB code and just see if possible.
okay. So we'll look at this maybe later. Okay, we'll discuss this over like email, or maybe I'll see what is the issue, and so I'll proceed with today's class so that we are able to cover the materials which we have planned for today. Okay, so I'll come back to you if we have time at the end of the class. We'll see the MATLAB code. Okay, and for question 5, we were supposed to use a lossy dielectric medium. So if we include a lossy media, the wave similarly propagates, gets reflected on the first interface, and you see that the amplitude of the wave keeps decreasing because this media is lossy. And then again reflection at the second interface. So in a lossy media, you'll see that the amplitude of the wave uh, like we it decreases. So again, please try it. If you have any issues, we'll come back to it. And then the last question was to modify the codes for sinusoidal sources. So you were just like, instead of using a simple Gaussian source, you just had to modify the e power the expression to a sine expression. So yeah, so this is not very difficulty if you try it. So these are the simulation results. Okay, I guess these two code, windows have been swapped. Yeah, so the middle one is actually for the lossy media, and the third one is the lossless. So that was all which was covered till yes, like till the last class, and then whatever we like was there in the assignment. So we'll start today's class with the calculation of the frequency domain output from our time domain results. So we are all familiar with the Fourier analysis, and uh, like we use Fourier transforms to move between frequency and time domain. And for discrete set of data, we use DFT, and uh, we uh, we are familiar with the technique fast Fourier transform, which is an algorithm that which is used to implement DFT in this like calculating DFT is tedious and more complex, and we have this like fast Fourier transform which can be easily implemented in uh, codes, and it can very fast calculate the DFT of a large set of data. So for our case also, we'll be using fast Fourier transforms, and there's some info, like this uh, thing for you. That Professor Gilbert Strang, is very popular within the mathematics community, and he had said that FFT is one of the like, most important numerical algorithm of our lifetime. So it was featured in this IEEE magazine, Computing in Science and Engineering. So we won't discuss like much about what is FFT, DFT, and thing. MATLAB has a function for doing FFT. If you are using Python, you can include the MATLAB library for doing the FFT. So we'll start with the code. The last class we had discussed all this. So we had this initial functions for clearing the window and clearing the variables. We had defined the simulation space as 500 with 500 nodes. The KC, which is the center of the space, was 250. The the two other sources at 150 and 350, which is KC plus 100, KC minus 100. So we have gone through all this, and like this is all the same which was there in the code which I shared. Now again, moving to the main part of the code where inside the loop, so we have the update equation for electric field. We have the frequency like for if we are using a sine source. This different types of sources, sinusoidal source, then again Gaussian source, and there's a third kind of source that we'll talk about is the windowed sinusoid, which is very uh, popular within the simulation tools. There are then over here at 47 we include the excitation in the electric field, then the boundary conditions, again the update equation for magnetic field, and then we are plotting the electric field over here. So this is all like discussed. Here are the like different functions to make the plot window, and then again. So what we do is before we end the loop, we choose the points where we want to see the where we want to record the data of the field. Like if we like for a wave propagating, and we want to see the FFT, if we want to see the wave in frequency domain, we record the values of the wave when it passes through that node. For example, okay, I'll use n. So we want to see the pulse which we are giving to the source in frequency domain. So what we do is every time the pulse value is updated, we store that into an array. And similarly, this if this is our simulation space, and ke is for example 1 over here, and ke is and the final value if it is ke, we what we do is we choose a point very close over here, and we record the value. So this is the, for example, over here when we are giving a source and the wave propagates from here to here, and we record the values over here. So we have kept this as so electric field at ke minus 5 gets recorded in extr. Then what we do is we once the loop ends, we have an array which has stored all the data of electric field at ke minus 5, and we have an array which has stored all the data of the pulse that we are giving to the at the source point. Now we start with the FFT algorithm. So we define the total length of the FFT. I've chosen as 4096. Remember, this should be 2 power. Oh my God. Oh God. So this should be 2 power n. Okay. So this is necessary for FFT. So that in FFT the data is split into halves, and similarly like the halves are split into halves, and then the algorithm performs its magic, and we get the frequency domain data. So make sure this is a multiple in the order of 2 power n. We What we do is and FFT requires the data to be complex, and what the data that we have accumulated over here, this is real. So what we do is we use this complex function to this is the real part, this is the imaginary part, and we are the imaginary part we are keeping it as 0 and storing it into a different uh, different array. And our since our simulation was run from 1 to n steps, so we have stored the entire values stored over here, from over here these two variables. Now what happens for the remaining parts, because n steps is less than okay, make sure this n steps is always less than or equal to the FFT length. So, and for example, we have stored from 1 to n steps, and now that there's a remaining part till 4096. This is the FFT length. So over here, we'll just fill it with zeros so that we have the entire array. So we from n steps to FFT length, we fill fill these two arrays with zeros. So we now have our final array which has the complex value of the time domain data. Is it clear till now, till this part? I believe yes. Am I still audible? And can you see the slide number 30?
Yes,
Yes,
sir.
sir. Yeah.
Okay. So till now, what we have done is inside the loop we have recorded the time domain values in these two variables. You made the variables complex, made the real values complex, and stored it to another variable, and filled the rest of the part with complex values of 0. Now we use the FFT function available with MATLAB. You can study more about it using the MATLAB help. So over there, the FFT function takes input the time domain data, the length of the FFT, and it supposedly asks you to normalize it with the FFT length. So yeah, so we for both the data, both the arrays, like both we perform FFT, we use the FFT length and normalize it with the FFT length again. And this thing that we are getting over here, this is the frequency domain data of the time domain data. So over here we have performed the FFT. So FFT is done over here. We have already got the frequency domain data. And over here, what I'm doing is I'm just finding out the maximum value from this source, and I'm using it to normalize it. Like I'm storing this value in M, and which I'll use it to normalize so that the maximum value which I see in my frequency domain window is 1. So this is not very necessary, but yeah, I do it so that it is easier to compare different signals. Yeah, so we have seen till over here in the last slide. Now, for plotting it, what we do is we take the dt, we multiply it with the 50 length and take it 1 upon so that we get a df. And this df, what we do is we use this df and then multiply it with this numbers and again scale it for gigahertz value and store it in frequency dat. So this is needed just to plot the frequency domain result. Okay, so you don't have to worry about much. You can directly use this because we like to plot any thing in MATLAB, you need the x and y coordinates. And what over here you have got is your y coordinate. And now what do you do about the x coordinate? You just cannot, if you just use the plot function with this, you'll get the data, but you won't be able to see what is there on the axis, is what frequency you are looking at. So this is necessary to like see the like for the x-axis. Now then we use the figure window. I've used subplot so that you get everything in one window. So over here we had recorded the x source and x transmitted values at the end of the loop. So we are so these are plotting the time domain things. I don't know. This is not working time. Okay, so these are plotting the time domain. The values of the source and the transmitted values. And over here, these are plotting the frequency domain. So we are using this frequency that this particular array as the x, this particular value, the c dat source. This is the frequency domain data that we got from using the FFT function. I'm using the absolute function over here to see the only the magnitude. Similarly, we do it for the transmitted value as well. So this is the plotting part. Any questions till now? Calculating the FFT, then doing things to the figure window. Okay.
No, I do not have any question.
Okay. So from the previous window, if we use a Gaussian source, so we get these are the time domain values which we recorded at the end of the loop. So so this is the pulse that we provided to the our simulation space, and this is what we recorded at ke minus 5. So you can see the pulse which started around 0 reaches around 500 at the k minus 5. So you can see at a later time we can see the same pulse, and when we perform the FFT on both of them, we get the same results because the FFT is independent of what is like how much delay is there in time. So yeah, so for the Gaussian source, we have this particular FFT. So the FFT thing works fine with the Gaussian source. When we use the sinusoidal source, so this is the pulse function that we are exciting at the source position, and it after around 500 time steps, the sinusoidal thing reaches the k minus 5 position near the the right hand boundary where we're recording it. So over here we get the we see the same sinusoidal function, and then performing in FFT, we see that both of them like are at this, like they're the same frequency. If I'm giving a source of 1 GHz, I see the same wave propagates, and if the frequency is same, we should get the same frequency domain results. Now, this is something very popular in simulators that are commercially available. If you use CST or HFSS, they they use this windowed sinusoid source. So what this source does is this it encapsulates the sinusoidal signal in a window, and so we have a signal which is limited in time domain and both in frequency domain. So yeah, so if you give a windowed sinusoid source of 1 GHz, uh, it propagates, and again after 500 time steps, you see it near the k minus 5 node, and forming an FFT, you get both of them at 1 GHz. So we have successfully used the time domain data to get the frequency domain data. Yeah, so that was all for the getting the frequency domain data from the time domain data. So any questions on that? Next, we'll start with the formulation using flux density. Maybe I'll go back to the code part that you can. Yeah, you can. I'll pause over here. You can look at the code, and if you have any questions, then we can discuss. Okay. So yes, Ankit. So your question. Okay, in the chat you have written, what is source and the transmitter? Okay. So if we go back to the next slide, so at so our simulation window has a source, right? Over here we are giving this pulse. This particular pulse, it generates from here and it travels towards the boundary, right? So this particular pulse is we are using the word source to denote it, and we are storing this particular excitation in one of the variables. And when this particular wave propagates, so I'm just using instead of I've used this the variable tr instead of I thought it as a transmitted wave, but you can call it as a receiver or something. So over here, you and over when this pulse propagates and comes over here, we record it over here. So for recording it, I'm using the other variable extr, and I'm storing everything in this variable. And for over here, I'm using exsrc. So the everything that is going inside pulse and everything that is happening over here is being recorded over here using these two values. So I store every time the pulse value get updated, I store it inside a array, and this particular n is what is driving the loop. So just in case, like if you want to relate it, so for example, if you were in your if you, there was a simulation space where you were using an antenna over here, and it was radiating, and you wanted to see what is being received at this particular point and this particular point. So what you could do is you could store the values, for example, at tr1 and over here as tr2, 2, and then you could perform an FFT on these two values and see what you received. And the excitation that you were feeding at the antenna could be your source. Any follow-up questions, Ankit? Okay. We'll wait for some more time. If anybody has any follow-up questions or any questions on how we went about getting the data from the loop and then storing it in a value and performing FFT. Okay. So I questions. We'll move towards the formulation using flux density. So up till now, what we did was we got our update equations using the Maxwell's equations, which had H and E. Now we can do we can also use D and H to write the update equations, and this is more preferred because if we want to simulate a media like which has losses and whose permittivity is function of frequency, it is easier to do it using flux density. So we'll first look at using flux density for a regular medium, and then we'll see how do we go about if it is a function of frequency. So our end goal is to model dispersive media. Okay, I won't write it because the cursor is not working fine. So our goal is to model dispersive media, and for that we need to use flux density. So we'll start with the flux density now. What do we do is instead of using E and using the epsilon over here, we start with the more general form of the Maxwell's equation, and where D is given by this particular equation. Now we begin with again normalizing it. So earlier we were using this equation. Now we also normalize the flux density. So the normalized density, these equations translate to these two are the Maxwell's equations, and again this is the normalized flux density related to the normalized electric field. Notice that we have the flux density and electric field written in frequency domain. Now, and this is since it is in frequency domain, it is a product in frequency domain. We will need to get the time domain representation of this equation. So we shift from frequency domain to time domain, and we are over here assuming a lossy dielectric medium. Now the electric field can the permittivity can be expressed using this expression. So this is like known to us, and we substitute this over here, and we get the flux density in terms of the electric field. Now what you see is going from frequency domain to time domain for this particular the first expression is easy, but for this we'll have to something more has to be done. So we have j omega over here, and which is equivalent of an integration in time. So the final expression in time domain is given by this particular equation, where this is translated to this directly, but and this changes to an integration in time. So this comes from the basic maths the change from the Fourier transform theories that we have learned. So we get this from this, and now we perform more simplifications on this. So we want to go to the sample time domain. Now this is continuous time, and now to go from the sample to the sample time domain, what we do is we approximate this integral into summation. So this particular integral is changed to this summation, and now we can see that dn and the flux value at nth time instant is dependent on the electric field value at nth time instant and all the electric field values from first to nth instant. Now to get rid of this particular summation, we separate this term and okay, so we take out the nth value and we get this expression over here. Okay, I scribbled it over here. So we have separated the nth instant and all the previous instants are given by this expression. Now we calculate the en. So what we do is we rearrange this. So dn comes over. So the dn comes over here. This particular expression goes over here. All the denominators are here, and this particular expression is over here. Now to we replace this by using we use a change of variables and we express this in terms of in minus 1 equals e power n minus e power I from I0 to n minus 1. And we now after replacing this, and this can this we can rewrite as in equals I n minus 1 previous value. What we have done is we have removed the dependence of the summation. So we have removed this summation and we have expressed this as a as a after change of variables, the ions will store the all the summation values of EA of the electric field, and the electric field now can be given in terms of the flux density, the summation thing I, and these variables. So I hope everybody was able to follow what we did. Like this was all maths and nothing very serious, just substitution and Fourier transform. I'll wait over here. If you have any questions on what we did, or if you want to go through it, we can wait and take questions. Anyone any questions, or if you want to read it, we'll pause over here. Okay, so change using a convolution. Yes, I think we will do convolution in the next page. Okay. Yeah, we can use convolution, but over here, I think it is simpler to just substitute this and perform Fourier transform on the individual terms. Convolution will also yield the same result. So maybe yeah, you can try using convolution. And in the coming slides, when we discuss about the dispersive media, we will use convolution over there. So we started with we expressed D in terms of E and permittivity. We had the expression of permittivity. We substituted it over here, got the expression of D in terms of permittivity, the term conductivity, and again electric field. We performed Fourier transform. Yeah, we performed the inverse Fourier transform. I believe. Yeah, inverse Fourier transform, and we got the time domain expression of flux density. we use this flux. We then use this sample time domain and approximated this integration as a summation, and then we used this summation. Then we brought this term outside of the summation and replace this expression, this summation by in, and then we expressed electric field in terms of flux density, in, and permittivity. And in is again a form of recurring term which updates with the current electric field values. So in is calculated from the previous in and the current electric field. So this is what we have got till now. Yeah. Okay. So till now, so we started with these two equations from Maxwell, and this is same as the previous cases. So we focused over here. We expressed the electric field so we'll use this and this as the update equations, and to calculate the E field, we got this expression which has in, and in can be expressed in terms of previous I values and E values. So using them, we will get our update equations for MATLAB and whichever program you're willing to use. So the T is calculated using this expression. Electric field is calculated again using this expression. I is calculated using this expression, and H is calculated using this expression. So nothing new. You are already familiar with how to write the update equations if you have something of this form for 1D. So these are the 1D equations over here, and the E field is calculated using. So this is all replaced by a variable GAX. So GAX over here, and D value and I value. And I is calculated from the previous I value, and this is replaced by GBX. So GBX over here and the electric field value. So any questions till here? So we have looked at how we, instead of using electric field, the Maxwell's equation having the electric field, we have used electric flux density and got the update equations. So using this also, you'll get the same results what you have discussed in the assignment. And I'll share the code for this with you, but in a few days, so that you can try using these expressions and write, like modify the code which I shared. So any questions till now? Am I audible? Maybe you guys lost me somewhere and I'm speaking to myself.
No, I can hear and it's fine so far. So we have to run the course to understand more about it.
Yeah. Okay. Any questions, Priyank, Ankit? So this was all like maths only, like just no only manipulations of the equations that we had. Uh, so if you even if you were not able to follow right now, you can go through the slides. I'm sure you will be able to. Everything is very straightforward. If you even if you have any doubts, we can go through it again in the next class. And once you got the this set of update equations on the left side, over here, once you had all these, we have already seen how to go from this expression, these equations to over here. Yeah, if so, if you can try using these equations and uh, try running the code, and you should get the same results when you were using EX and HY. So we'll now look at the frequency dependent media. So up till now, we we have seen how we use the electric flux density instead of the electric field for the formulation of the update equations. Now we'll modify them for frequency dependent media. So most media, they like the proper their dielectric constant and conductivity vary with frequency. So up till now, whatever we were simulating, the media properties were not function of frequency. But what if they were function of frequency? So we have to come up with something. So we'll start with okay, I'll use a pointer. Okay, so we start. So we'll start with a medium whose dielectric constant and conductivity vary with frequency. So this is something. So I've borrowed this picture from the textbook of Sullivan. So the dielectric constant is given by this particular like it varies in this fashion. With it decreases with the frequency and conductivity increases with frequency. Uh, so for a media whose like the properties vary, permittivity is varying with frequency, it can be expressed using what we call as a Debye model or Debye formulation. So over there, we express the permittivity using this particular expression where sigma is the conductivity, and this and we have an additional term which is also a function of frequency. The tau is the relaxation time and chi1 is another. So for a media whose material property the permittivities as a function of frequency is expressed in this form. So you can study more about the Debye formulation. We won't spend much time on this because this is something related to materials. But if, for us, we have this particular function is known to us. That we know that using the Debye model, I can express the permittivity as a function of frequency in this particular fashion. And for a given material, all these values will be known. This sigma, the chi1, tau, epsilon naught, epsilon r, these are known for a given media. So once we have these values and we have this expression, we can use this particular expression to model our FDTD simulation space. So we already have this Debye formulation with us. And the only extra term that from the previous formulation that we have now is this third term. So our discussion right now will be centered around this third term because we have already discussed for the first what happens if our permittivity was given by only the first two terms. So we will define the product of the last term and electric field as S omega. So we have this. So S omega is given by chi1 plus j omega tau electric field as a function of frequency. Uh, okay, so this is what we have now, and this again is in frequency domain. Now we have to go to time domain. So if we look closely, the inverse Fourier transform of the first term is very simple, and this can be given by this expression. Okay, and similarly for e omega, its inverse Fourier transform is given by et. So we know the inverse Fourier transform of the first part and the second part, and now we need the inverse Fourier transform of the entire thing. So over here we'll use the property of convolution, and now st is given as the since this is a product in frequency domain, we can give this we can find the its inverse Fourier transform using the convolution, and it is given by this expression. So we had the we have s omega in frequency domain. We got the s omega in time domain. Now again, this is in continuous time. So we need it in the sampled form. So we will approximate the integration as a summation. And okay, so you don't have to worry about this. This looks very scary. Uh, so you can take your time and read this. This is not very complex. So we have just changed this integration to summation. And if you you can see that now Sn can be expressed in terms of En, and again the summation of all the values of electric field from previous time. So to remove this dependence of storing the value of electric field at all the previous time, we will use what we do is we calculate the value we calculate the value of Sn minus 1, and what we see is that we can give Sn in like this. And now we use this particular value of Sn and substitute it back into the first expression, and the final expression for Sn can be very simply given in terms of the previous values of Sn and the current value of electric field. So I'll pause over here. I'll let you read the expressions. This is all just very math which is written in a very difficult form, but it is very simple. You can read this. So right now we are focusing on the third term of the permittivity and trying to express like get the time domain form of the third term. And for that, we introduced a term Sn to introduce a term S, and to get its sample time domain form, we have done all this calculation and tried to get Sn. Any questions on this? Okay. So till now we'll go back. So we had the d by formulation. We know how to solve it for the first two terms. The third term is expressed in terms of S over here. This is in frequency domain. We are trying to get the time domain form. We know the individual Fourier inverse Fourier transform of the two terms. We use the convolution technique over here, and then we approximate the integration in terms of summation. We substitute the value of Sn minus 1 in the expression of Sn to get the final expression for Sn. Now you have to recall from the previous formulation that we did. Over there, we had the permittivity given by this expression, and we had expressed the flux density in terms of electric field and the permittivity, and then we had got this particular some expression for dn, where the third term was expressed by in minus 1. Okay, so if you recall how we got in, now we will directly use this in thing over here. So again over here we have d as a d expressed in terms of permittivity and electric field, and the permittivity is given by one additional term over here. Now this first term can be approximated by using in. So sorry, the second term by in, the third term by Sn, and we substitute both of them back into the this d over here, and we get this final expression for uh, the flux density in terms of the electric field and in and Sn. So I'll wait over again pause over here, let you read the expressions. So the expressions on the right hand side is what we derived in the previous like derivation, where we're focusing on getting the update equations using flux density. And now we are using the same concept of using the flux density to formulate a frequency dependent media, and just that the expression for the permittivity has changed. Now we have an additional term, and we did the calculations again for the third term, which is now being given by Sn. Any questions, anyone? Okay, so we'll proceed from here. Now that we have already got the expression of the flux density in terms of electric field and these two other terms, we try to express the electric field in terms like we solve it and try to express the electric field in terms of the flux density and I and S. So this first expression is giving me like the solution for electric field in terms of flux density for at the same time instant and the in value. So like this contains the summation of on the like the values of the previous time instants, the again Sn, and we already have the everything in the denominator is known to us. We know the time step, we know the relaxation time, chi1, epsilon naught, epsilon r, sigma. This is all known to us. And what about the I and Sn? So for them also we have the updated equations over here. In can be expressed in terms of the past in value of in and the electric field value. Similarly, Sn can be calculated from the past value of Sn and the electric field value of the current instant. So now we have the I and S, and from previous and the using the Maxwell's equation for D and H. Okay, I'll switch to pen. So this and this is same when from the for the Maxwell's equations. So this is the same equation of having. Okay, again the cursor is d by dt. This is same as d by dt equals and d. Okay, and this one is dh by. I can't write it. Again, this is dh by dt. Okay, so these are the Maxwell's equations for 1D, and this E is calculated from here. This I is calculated from here, and Sx is calculated from here. So we get this 5 set of update equations for frequency dependent media, and again we have substituted this particular thing is calculated as GAX over here, and this is calculated as GBX, and this is calculated as GCX, and over and this particular expression I think is given over here. So yeah, so we have substituted everything like we have once we got the update equations over here, we just simply wrote them for the computer. Now you can use these equations directly to get the frequency dependent to simulate a frequency dependent media. So I won't be showing results today. These are the update equations. You can I'll recommend. I know it is holidays and you won't have time, but if you find time, I will recommend just modifying the MATLAB file to for these particular set of equations and see what happens. And I'll discuss the results and the code in the next class. Yeah, so that was all that we covered today. So any questions if you have for the frequency domain, calculating the frequency domain results, formulation using the flux density, and formulation for a frequency dependent media. So we'll so that's all that I wanted to cover today. So if you have any questions, we can take the questions now. And any questions from the previous classes as well.
Well, I don't have, we'll ask the questions for today's class next time. But I still have a
Okay.
question about the previous class. What happens if um, Kc plus 20 and Kc minus 20, when we replace it in the source, then the wave
Okay.
goes much above the amplitude. And also with Kc plus 50
Okay.
and
So
minus.
if nobody has, yeah. So if nobody has any questions on today's class, then we'll stop the class for today and we'll discuss Jay's question. Okay, so Abhishek is saying that he missed today's class, and to that okay, I'll upload the video and the slides today itself, without delay. Yeah, yeah,
Thanks,
Abhishek,
Anand.
I'll do that. Uh, okay, so I'm sorry you missed your class. I should not have scheduled a class on the holidays, Christmas Eve.
No, 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 no.
But
Actually, I
again,
did some part. I
uh,
had I missed some. No problem. Classes are fine. No problem.
okay. Okay. Okay, so we'll close for today's class and we'll go to Jay's question, doubts on the assignment. Yeah. So Abhishek, again, since you missed your class, today we discussed the assignment, and then we discussed the frequency. How do we get the frequency domain results from the time data? We went through the MATLAB code for performing FFT, and saw results using Gaussian source, sine source, and windowed sinusoid. Then we started with the frequency dependent media um, and the reformulation using flux density. So up till last class, we were formulating the update equations using electric field and magnetic field. Over here, instead of using the electric field, we use the electric flux density and the magnetic field. And using them, we formulated the update equations and we calculated the electric field from the electric flux density. So that is all we did today. And moving as once we had formulated the update equations using the flux density, we just modified the permittivity expression to get the uh, to simulate a media whose permittivity and conductivity were a function of frequency. So that's all we covered today. And the next class will start with the FDTD in 2 dimensions. The perfectly matched layer. I'll see how much we'll be able to do in next class, but this will probably take 2 to 3 classes. Yeah. So, and we'll then again, since we already know how to get the frequency domain results, now we'll look at the frequency domain results as well to get this total and scattered field formulation in 2D. So I had shown you one of the simulation space where I told that what happens if you have a source over here and you want to see the field values as they propagate at 2 different points or 3 different points, or if you have for example, a dielectric medium, and what happens when a wave propagates, hits it, and you see the transmitted wave that reaches them at these particular locations. So all this can be done in 2D. So we'll see the FDTD in 2 dimensions in the next class. Okay, so we'll go to Jay's question, and I'll open MATLAB, and Jay, you can tell me where you modified the code and see. Okay, so where is let me open the code which I shared. So yeah, this was the code which I shared. Can you tell me the line number where you made the modification?
Can you please go up maybe around 40, line number 40 around somewhere. Okay, here on line number
Line
47,
number 40.
47, 47.
47. Okay,
Yes,
47.
yes.
Yes.
If you change it to Kc plus 20, and then please look at the result.
PC plus 20. And which source you were using? A Gaussian source?
Yeah, exactly the same which you sent me. Yes, the Gaussian one.
The Gaussian source. Okay.
Yeah.
I'll check everything is fine over here. Again, the KC is 20. at 250. And over here we are using Kc plus 20, Kc plus 20 and pulse. Okay. Are you able to see the simulation?
No, not the result. I can't see the animation.
You're not able to see the result?
No, no.
Okay. Let me stop and share my screen again. I'll share the entire screen now. Can you see it now?
Yeah, I can see the screen. Okay. Yeah.
Okay, so the simulation already passed, so I'll perform the simulation again. Okay, so I made you can see the port line of 47, right? So this is okay to you, right? This is what you have done.
Yeah, for Kc plus 20. Yeah. Just a minute. Oh, I think it's fine. I mean, I made a mistake. Sorry.
Oh, it's fine. It's
Okay.
fine. Yeah, this happens. Since a lot of expressions and underscores and things are there, I know I've missed some places. You miss some symbols, and then something goes wrong, and you are not able to like detect. So it's fine.
Yeah. So the
So I'll
problem.
again run this session, and you can see what happens. And okay.
Yeah. Okay. All fine. Okay. Thanks.
Yeah. Any other question? Any other doubt?
And we are having a lecture tomorrow, right?
No. Sorry, I forgot to like announce. So no lecture tomorrow. I'm already feeling very much guilt that I had to keep a lecture on the Christmas Eve. No lecture tomorrow. No lecture on 31st and 1st. Enjoy your holidays.
Next
I
time when are we meeting?
won't
Next
bother
time.
you all with my classes on. Yeah, come again.
Next time when are you going to meet?
Next, when we are going to it.
Yeah.
Yeah, I should tell that. So next class will be on 7th.
7th January.
7th January. So we'll
Oh,
meet.
wow.
Yeah. So unfortunately, we have the New Year Eve and the New Year on Saturday and Sunday.
Yeah,
So I won't be like keeping classes on the New Year Eve. And even if I keep it, I guess nobody will come. So it's better that we do a class later and meet in person.
yeah.
Meanwhile, I'll send out the a second assignment. Maybe you guys can try if you have time. Otherwise, it's fine. It will be, and since you have time and you can maybe go over the previous lectures, find out any doubts that you have. Very good time to go through the textbook if you have time. We have already covered the chapter 1 and 2 from Sullivan, and chapter maybe 1 or 2 I don't recall from David B. Davidson. So you can go through them. David B. Davidson has formulation on transmission lines as well. So right now maybe you can skip it, or if you are feeling like it, you can go through that as well. Yeah, you can do all these things if you have time, but I guess you won't be having I'm not sure. Yeah, so we'll meet on 7th. Next class will be on 7th.
Yes, please upload today's material. Thank you.
Yes. I'll do that after the class, after we end the class.
That Sullivan book also has a MATLAB code, or only because I saw C plus plus or C.
So there are two books by Sullivan. Yes. So one has a code in C or C++, and the other has code on Python. So not in MATLAB, but if you are familiar with maybe C or Python, you can refer to one of them and use them to write your codes in MATLAB. So the update, especially the book in the book with which has Python code, has almost similar like update expressions and everything compatible with MATLAB. You can just copy and paste it, but some equations will need modifications. But
So
if you are able to follow the lectures, I think it won't be an issue that for translating the Python code to MATLAB code. Once if you understand the code.
yeah, I ran some of the codes from Python. It worked and everything was fine, but the animation part, I have to do how to do animation because there was no animation plot in the Python.
Yeah, yeah. So for generating the animation thing, you can the plot window automatically, if it is inside the loop, it will update. And if you want to record it, I'll share the code. Like you don't have to worry if you want to share your results.
Yeah, yeah, yeah. Please.
So it is a simple reading writing inside a file, and the file is an MP4 file. So it's a video file that you are reading writing into it. Okay, then if you have any questions from like up till like whatever we have discussed in the last, including today's the four lectures, we can maybe discuss now. Or if you have any questions on the about the class itself, like how where we are going, or something that like that, or if you want me to discuss any particular thing. I remember Jay, you have asked me to discuss about FEM, FIT, FDTD in general. So I'll try to include that in the next lecture. Anything other than that, maybe you can let me know now or via email. I can try to incorporate them in the lectures. Okay, then I'll stop the recording now.